Hi, Chemistry. This is Mrs. Ellsworth. We're going to be talking about the atomic theory in all of Unit 3. But this section of the video is just going to be talking about the early atomic models. And it's going to take over a period of 2,600 years. And so let's go ahead and get started with the very first theory. Democritus and Lippicus, I think is how you pronounce the other Greek, they believed that you could divide something and divide it and divide it and divide it, and eventually you get down to one small unit. This unit they called the atom. It is the very first time that that word has ever been used that we have, in history written down, and that this word meant indivisible. So in other words, you couldn't divide it anymore. So it was got down to one small unit, the atom. Anyway, what happened though in Greek back then, that they never did any experiments. Okay, they only debated. They were all philosophers, and so they would talk about it, and whoever was the better speaker would really be the one who was right, according to them. Anyway, so they didn't do any experiments, and so what happened is that there was a group of atomists. They believed that everything got down to one small basic unit, and there were those who believed that, hey, everything is made up of 4 different elements. Earth, which may had sides that were held against one another. Fire, was prickly and it would hurt, and water was spherical so it could flow easily, and air was something light. Anyway, so they believed that they could be divided up infinitely, and they also believed that everything was made up of a certain ratio of those 4 elements. Now again, the atomists believed pretty much more like what the modern atomic theory is, that everything could be divided down to one unit of that substance. Okay, not just those 4 elements. Now Aristotle was involved in this, and he also debated too. And he said, hey, if everything is made up of atoms, then why doesn't everything wither away like sand castles do? And sand castles, they just kind of fall apart. And so he believed that if everything was made up of these small atoms, why didn't they fall apart? Because rock and stone is very, very solid, and of course it doesn't wither away real quickly. So that kind of put a kibosh to the Greeks using the atomic theory. So then we skip to the late 1700s, where there's 3 basic laws. I mean, Lavoisier and several other scientists are creating laws that they're finding to be true each time that they test them over and over and over. Is a law of conservation of mass. Now, sometimes that you think when a chemical reaction occurs that stuff just kind of disappears. And it's not true. They're actually finding out in the late 1700s that, hey, when you burn something, carbon dioxide is leaving. Also, they're finding that, and they were able to figure out that these molecules that leave are actually part of the mass that was in the original chemical reaction. So it's saying that the chemicals are not created nor are they destroyed. They're just really changing, either physically or else chemically they're changing. Anyway, here are some examples of the law of conservation of mass. A carbon plus an oxygen yields carbon monoxide, and that happens every time. And it can also go backwards too, where they're split up into carbon and oxygen. Okay, now there's the law of definite proportions. That's the fact that chemical compounds contain the same elements, exactly the same proportions by mass, regardless of the size of the sample that you were given. So in other words, your proportions stay the same. I'll explain that a little bit more. Let's look at the law of multiple proportions. If 2 or more different compounds are composed of the same 2 elements, we're talking about a ratio change here. So let's look at an example. So we've got 1 carbon is combined with oxygen, and it creates carbon monoxide every time. It's a 1-to-1 ratio. Now here is a 1-to-2 ratio. You've got 2 oxygens combined with 1 carbon, and every time you will get this 1-to-2 ratio. And so that is the law of multiple proportions. Here's a 1-to-1 ratio. Here's a 1-to-2 ratio with the same elements. Now, John Dalton in 1808, he proposed an atomic theory that uses these 3 laws. He did many experiments back in 1800. He did many experiments to help him find his atomic theory. Now, he used 5 postulates that helped describe his atomic theory. That all matter, everything, air, solids, liquids, gases, everything is composed of atoms. Also, the atoms of the same element have the same size mass. Okay, all nitrogens are exactly the same, but they are different from others that are not nitrogen. Okay, atoms cannot be divided, created, nor can they be destroyed. That kind of sounds like a law, doesn't it? Okay, also atoms of different element combined in simple whole number ratios. Well, you can't have a half a carbon atom reacting with something. So that's why they want whole number to create whole number ratio in the chemical compound formulas that we've talked about. Now, in chemical reactions, atoms are combined, separated, or rearranged. Okay, and these are all encompass those 3 laws on the previous slide. He also believed that the atomic theory, what it looked like is that all the atoms were all little round spheres, and then nitrogen spheres or atoms looked different from oxygen spheres. Then 100 years later, almost 100 years later, J.J. Thomson, he is working in England, and many scientists are working with the cathode ray tubes. Anyways, it's got this stream of particles that is hooked up to a battery here, okay, and a stream of particles, okay, that he later on figured out were electrons. He concluded this because he would go and stick a magnet up to it, and it would go and make this trail bend, okay? And then also he would go put a negative source next to it, and he'd watch it bend away, so it would deflect away from it. So he knew that whatever these negative particles, I think he called them corpuscles, anyways, that they would deflect and move away from a negative. He knew that they had a negative charge. Anyways, the name corpuscles didn't ever stay with it, but electrons became the term for it. Now, I just wanted to point out that cathode ray tubes are the old-fashioned big tube television, and that's not very popular anymore. We're kind of all getting flat screens. Anyways, with Joseph Thomson's theory, he kind of said, hey, Dalton's theory, this is going to change here soon. Anyway, he and other scientists, they knew that atoms were neutral, so that when he discovered the electrons, okay, he knew that there had to be a positive mass with it. And so this big blue area here is all a positive mass, and then the electrons are stuck on the outside and within it. He called it a plum pudding model because back then you would have plum pudding, and it's kind of like a cake type dessert that had plums within it. And so he created this model to describe what this atom looked like. And so now modern day, I'd say maybe chocolate chip cookie dough is where the chocolate chips are the electrons and the dough part is the positive mass, because they knew it had to be neutrally charged. So since now there are parts of an atom, that means that Dalton's theory is not, it's changing away from it. Okay, so in the older, earlier days of the atomic models, it went from 4 different types of elements to Dalton's models of small spheres, and now to Thomson's model with electrons within it. And that's it.